Okay, so let's talk about solving problems for equilibrium. So we're always going to act for an extended object like its mass is at the center. We're going to put the axis at the location of an unknown force, if possible where there's more than one unknown force to cancel out the torque. And then we're going to have three equations. The net force in the x direction is 0, the net force in the y direction is 0, and the net torque is 0. And remember, clockwise torque is negative, counterclockwise is positive, and so we can get negatives and positives adding up to 0. So to solve the problem, our recipe is to draw a free body diagram showing all the forces acting on the object and where they act, and then break the forces into components. For this day, we're going to only do one-dimensional problems, so the forces will all be in one direction. We don't have to do any components. And then we're going to start off by writing that the net force is 0. And then we're going to choose the axis for the torque and write the net torque is 0, and then use those equations that we have, either 2 equations for 1 dimension or 3 equations for 2 dimensions, and solve to get the unknowns. So in this problem, we'll start off with something very simple. We have a 20 kilogram child sitting 1 meter from the center of a 3 meter long seesaw. So here I've got a 20 kilogram child, and they're of course going to have a force downwards that's equal to their weight. I'm going to put the 20 kilogram kid on the left side. It doesn't say which side they're on, so I'm going to write that their mass, I'm going to write that ml, and their distance RL of 1 meter from the center. Then I've got a 30 kilogram kid on the other side, and they're going to have their weight downwards. Okay, and their mass is 30 kilograms, and their distance from the center, I'm going to call it R from the right, we don't know. So we know R left is 1.0 meters. The mass on the left is 20 kilograms. And so the force on the left is going to be mlg. So it's going to be 20 times 9.8, or 196 newtons. Okay. On the right side, we don't know the distance. We know the mass on the right is 30 kilograms. And so the force on the right is going to be the mass on the right times g. So that's 30 times 9.8, or 294 newtons. All right, so what else do we have in terms of forces? Well, we have 2 other forces, right? We're going to have the mass of the seesaw downwards, and we're going to have a normal force from the fulcrum upwards. That normal force is what's going to keep things from falling down to the ground. All right, so what do we do? Well, first we do that the sum of the forces is 0. All right, so our recipe is the sum of the forces is 0. So what do we have? We've got normal forces up. We've got the weight of the kid on the left down, the weight of the kid on the right down, and the weight of the seesaw down. So that adds up to 0. And since they don't tell us here the weight of the seesaw, we're sort of stuck at this point. Can't do anything. So let's go on to the torques. So the sum of the torques is 0. Now where am I going to put my axis? So I want to put my axis where I have forces that I don't know. So I know the weight of the 2 kids. So let's put the axis at the center of the seesaw. So at the fulcrum. And then that means that the torque from the normal force will be 0. And the torque from the seesaw, let's call it tau s, will also be 0. Why will they be 0? Well, remember, torque equals Fr sine theta. And so if our R is 0, which it will be if we're right at the location of the axis with the force, then the torque is 0. Okay, so we're only going to have two torques here, one from the left and one from the right. So let's do that. So torque from the left is the force from the left times the distance from the left times sine of theta. What's the angle? Well, the angle is going to be the angle between R and F. And if you look at the picture, R is horizontal, the force is vertical, so it's going to be 90 degrees. Okay, so we've got our force, 196 newtons, times 1 meter, times the sine of 90. Sine of 90 is 1, so I could just ignore that. So 196 times 1 is 196 Newton meters. Okay, what's the torque from the right? Torque from the right is the force on the right, R on the right, sine of theta, and again the angle is going to be 90 degrees. We know the force is 294. We don't know the distance, and sine of 90. So I'm going to get 294 times whatever the distance is that the heavier kid is sitting from the center. Okay, so those two torques, torque on the left plus the torque on the right, that has to add up to 0. So if it's going to add up to 0, one of those has to be positive and one of them has to be negative, right? So how do I figure out which is which? But what I usually do is I'll put my pencil on the screen or on my sheet of paper, and I'll hold it at the center in this place where my axis is. Now, if I pull down on the left side of my pencil, the way that the kid on the left is sitting, what happens? Well, that makes the seesaw rotate counterclockwise, so that's going to be a positive torque. Okay, what about the kid on the right? Well, if I pull down on the right side of my pencil when I'm holding it at the center, the pencil will rotate clockwise, so that's going to be a negative torque, so it's clockwise. Okay, so my equation is that 196 minus 294 times the distance on the right is equal to 0. And so now I can solve that. I've got one equation, one unknown. So the distance on the right is 196 over 294. So that's going to be 0.67 meters. Okay, so pretty straightforward here. We didn't really have to use the force equation. So next we're going to do a problem where we have to use the force equation. Okay, so now let's do another problem, and this sort of bridge problem is really standard. So you have problems that look like this with a kid on a diving board, or painters standing on a scaffold. This is a very, very typical problem, and make sure you know how to do this kind of problem. So let's say we have a 10,000 kilogram bridge that's 10 meters long and it's supported at each end. Now we have a 2,000 kilogram car sitting 3 meters from the left side, and we want to know what are the supporting forces at each end of the bridge. So if you're an engineer, this is the kind of thing that you need to consider. So let's first of all start off. Our recipe is draw the picture showing the forces. So what do we know? We know we've got a support on each end of the bridge. We know the bridge is 10 meters long, from left to right. Let me draw that at the top so it doesn't get in the way. All right, and we've got a car. All right, here's my art skills. The car is sitting 3 meters from the left end. All right, so we want to know what are all the forces in this picture. All right, so I've got, what do I have? I've got the weight of the car. I don't know, let's call it the mass of the car times G. And we know the mass of the car is 2,000 kilograms. What else do we have? Well, we've got the mass of the bridge, right? The bridge is 10,000 kilograms, so let's call that MB for the mass of the bridge. And where is that going to act? Well, it's going to act halfway along the bridge. So it's going to act right at the center of the bridge. So I'm going to have a mass of the bridge times G downwards there. And let's see, how far along will it be? Well, it's at the center of the bridge, so that'll be 5 meters along. So obviously I didn't quite draw that to scale, did I? Okay, so what else do we have? Well, we've got those two downwards forces. What's keeping the bridge from falling down? Well, we've got a force on each pillar at each end of the bridge. And let's call it the force on the left and the force on the right. Okay, so we've drawn a picture showing the forces. The next thing we have to do is to do that the net force is 0. Okay, so we only have forces in the y direction, so we're going to just draw our forces. So the net force in the y direction is 0. So what do I have? Upwards, I've got the force on the left plus the force on the right. And downwards, I have minus the mass of the car times G and minus the mass of the bridge times G. So let's figure out what those are. So the force from the car is going to be 2,000 mass times 9.8. So that's going to be 19,600 newtons. The force of the bridge is going to be the mass of the bridge, 10,000 times 9.8. So that's going to be 98,000 newtons. Okay, so what we have is that for the forces, the force on the left plus the force on the right minus 19,600 minus 98,000 equals 0. And right now we can't solve for that at all because we have two unknowns in there. So all we can do is we could bring all the numbers over onto the right side. So the force on the left plus the force on the right is equal to 19,600 plus 98,000, which is 117,600. Oops. Newtons. Okay, so how am I going to find it? Well, I've got two unknowns, the force left and force right, so I need two equations. And the only other equation we have for a one-dimensional problem is the torque equation. So what am I going to do? Well, I'm going to have to choose an axis. I'm going to choose my axis at a location where I have an unknown force. So the two unknown forces are left and right. Let me just put the axis, I'll draw a red X at one end. I'll put the axis at the left end. Okay, so how many forces do I have here? I've got 4 forces. I've got force from the left, force from the right, weight of the car, and the weight of the bridge. So I'm going to have 4 torques. But I know the torque from the left side is going to be 0. What's the torque from the right side going to be? Well, it's going to be FR sine theta. And for these one-dimensional problems, the angles, so let's look at the picture there. I'm drawing in the angles. The angle between the force and the bridge is always 90. So we can just ignore theta is always going to be 90. So sine of 90 is 1. So I'm just going to leave that out of the equation. So it's just going to be the force times the distance. So it's going to be the force of R. And how far is that FR from where I put the axis? Well, the axis is at the left end. So it's going to be 10 meters. Okay, so that torque is going to be 10 times Fr. Is that torque going to be positive or negative? Well, what I do is I take my pencil, I'm going to hold my pencil at the left end, and if I pull up on the right end, which direction does it rotate? Well, it makes my pen rotate counterclockwise, so that's going to be a positive torque. All right, torque from the car and torque from the bridge are the other two torques that we have to do. Okay, so torque from the bridge is going to be torque from the car is going to be the force from the car times the distance of the car, and it told us that the car was 3 meters from the left end, and that's sort of why I chose to do it from the left end, because I already knew the distances. All right, so it's just going to be 3 times 19,600 clean that up a bit. And the force from the bridge is going to be the force of the bridge times where it acts. It acts at the center, so that's 5 meters away. So that's going to be 5 times the force of the bridge, 98,000. Okay, are those going to be clockwise or counterclockwise? Well, again, take your pencil, hold your pencil at the left end. Now if you pull down where either the car or the bridge is, that makes your pen rotate clockwise, so that's going to be a negative torque. All right, so next thing we have to do is to put in the numbers. I can throw that in the calculator if I want, and then add up those torques and set it equal to 0. So what do I have? I've got minus 58,800, and I've got minus 490,000 Newton meters. And again, remember those are net minus because they're clockwise. All right, so if I add those all up, they have to add up to 0. So the sum of the torques is equal to 0. So 10 Fr minus 58,800 minus 490,000 equals 0. So that means that my Fr is just going to be 58,800 plus 490,000 divided by 10 if I rearrange that equation. And so I get that my force on the right hand side of the bridge is equal to 54,880 newtons. Okay, so I've got one of my unknowns. Now I can take that and put it up into my equation from the forces and find what my force on the left is. So my force on the left plus the force on the right, 54,880, is equal to 117,600. So that means the force on the left is equal to 62,720 newtons. Okay, and in this problem, how many significant figures do I have? Looks like I've got about 2 sig figs, so I should make this 55,000 newtons for the force on the left and 63,000 newtons for the force on the right. So the steps are always the same when you solve the problem. Draw all the forces, write that the net force is equal to 0. Usually that will leave you with 2 unknowns still. then get another equation by writing the torque equation. The torque equation will give you one of the unknowns that you can put back into your force equation to give you the other equation. So the problem that you have to do is very similar to the one that I just did. We've got a uniform plank carried by two people, and in this case the only thing that's different is that one of the people isn't right at the end. So Abe is holding the left end of the plank and Mary's half a meter in from the right end, and we put a brick that's 1 meter from the left end. So it's going to be very similar to the bridge problem. So see if you can solve this one-dimensional problem.